Hello everyone. So, in the previous lecture we have discussed different CVD techniques, that is chemical vapor deposition techniques, and we also have seen that chemical vapor deposition has certain advantage over physical vapor deposition, and one of the major advantage is like a conformal deposition. If you have a pattern substrate, it has a better step coverage. However, it varies from system to system or reactor to reactor or process to process, because CVD also can be classified into different processes. For example, it can be atmospheric pressure CVD, it can be low pressure CVD, or it can be say plasma enhanced CVD, so on and so forth. So, we have seen that CVDs can be classified in different processes based on the pressure involved in the process or based on the stimuli. If you generate plasma, or if you form plasma inside the chamber, then it is like plasma enhanced CVD. One of the advantage of plasma enhanced CVD is it's a bit low temperature process. Usually chemical vapor deposition is a high temperature process, but in certain cases, for example, if you use polymer substrate, if you use biomaterials or organic materials, you need low temperature process. So, in that case plasma enhanced CVD will be useful. So, we have seen these details in our previous lecture. Now, briefly we will see what are the different advantages and disadvantages associated with the CVD techniques that we have studied. So, we have studied atmospheric pressure CVD, we also have studied low pressure CVD, and we have seen what is plasma enhanced CVD. Now, we will see what are the different advantages and disadvantages associated with these techniques. So, in case of atmospheric pressure CVD, it is comparatively low temperature process and the deposition is fast in case of atmospheric pressure CVD, and the reactor is simple. It is not a very complicated reactor. However, the disadvantage is the step coverage is poor in case of atmospheric pressure CVD, and it also has a disadvantage of particle contamination. So, it may introduce some sort of contamination in the deposited layer. So, usually low temperature oxides we deposit using atmospheric pressure CVD. However, in case of low pressure CVD, the purity is excellent. This is one of the advantages. The uniformity is good in case of low pressure CVD. It has a conformal step coverage. So, the step coverage is better, and it has a large wafer capacity. That means it can help us to deposit film in a batch process. So, you can put lot of wafers in that reactor. Disadvantage is it is a high temperature process. So, the temperature is usually high. So, if you want to use a polymer substrate or say organic material, then probably low power CVD or low pressure CVD won't be the best choice. Then in this case the deposition rate is comparatively less. So, these are the disadvantages. So, usually high temperature oxides, silicon nitrides, both doped and undoped, then polysilicon, these are the materials that can be deposited using low pressure CVD, not low power, it is low pressure CVD. Okay. Then we have plasma enhanced CVD. In plasma enhanced CVD we have a better step coverage because there is a plasma present. So, you can understand that the reaction will be more uniform across, and then the deposition is fast. In this case, it is again a low temperature process. We have seen the temperature is comparatively less in this case, but the disadvantage is it creates lot of byproducts which may introduce chemical or particulate contamination in the deposited layer. So, one has to be very careful as far as the contamination is needed. So, usually low temperature insulator over metals, or for passivation, in order to put nitride, passivation we will see in the coming slides what is a passivation. So passivation is like you make a surface non-reactive just by coating a different material on top, for example say nitride. So for passivation purposes PECVD is useful. This is a kind of comparative study between different CVD processes. So some has certain advantages, some disadvantages. So based on that you decide which process to use for deposition while you are interested in a CVD process or CVD deposition for a device or sensor fabrication. Not only in CVD process, you will see there are certain advantages and disadvantages in various other processes like ALD, physical vapor deposition and chemical vapor deposition. ALD is a kind of chemical vapor deposition which is known as atomic layer deposition, that is what is ALD. PVD is physical vapor deposition, we already have studied, and then we also have chemical vapor deposition. So if you see step coverage, we have seen that for PVD, physical vapor deposition, it's very poor because it's like a directional deposition. If you have pattern of this sort and then if you have a source, because it's directional, sort of line of sight deposition, so you will find here the deposition is not that good, right? Or maybe in these edges also it will not be very nice deposition. So it's a non-conformal deposition, that's why step coverage is very poor. However, in case of ALD, step coverage is excellent. But in case of CVD, it varies. It depends whether you are using APCVD or LPCVD or PECVD or some other CVD. So in certain cases you will find, for example, for low pressure CVD, the step coverage is better. However, in case of atmospheric pressure CVD, maybe the step coverage is not as good as it is in case of low pressure CVD. So it varies, depends on the process that are involved. Then deposition rate for both physical vapor deposition and chemical vapor deposition, the deposition rate is excellent. However, in case of atomic layer deposition, it's kind of acceptable, it's not very less, it's like moderate. Then thickness uniformity. What do you mean by thickness uniformity? If you have a substrate and if you deposit say 100 nanometer layer on top of that substrate of any material, whether you get 100 nanometer throughout the surface or not, if it's a large area, across the area you are getting enough uniformity or not, everywhere it's 100 nanometer or it's somewhere 90, somewhere 110, something of that sort. So uniform thickness uniformity wise, both PVD and CVD are excellent. Even atomic layer deposition also is a kind of excellent process. So as far as the thickness uniformity is concerned, you can use any, say atomic layer deposition, physical vapor deposition or chemical vapor deposition. Material availability, in case of physical vapor deposition, it's excellent. You will find those materials, they are more kind of commercially available. However, in case of CVD and ALD, you need to first figure out what are the gases that are needed, that you need to insert. So it's like acceptable. Every time you may not find all the gases that you need, may not find all the materials that are required, but it's acceptable. Mostly you will be able to figure it out. As far as the defects are concerned, defects meaning if you deposit a layer, just I have shown over here, whether there are some defects or not, whether the layer is like having some defect like this or not. So defects wise, ALD, atomic layer deposition is acceptable, it's moderate. PVD is like poor, and in case of chemical vapor deposition, again it's like moderate. Okay, so this is a kind of comparison that I have shown just to give you an idea that there are different processes or deposition processes, deposition techniques are available, but one has to choose a deposition technique based on all these parameters, what the device engineer wants, what the sensor engineer wants, what a researcher wants. So based on that you can choose what process is suitable for certain device fabrication or sensor fabrication. Now the next topic is patterning. Once you have the deposition technique with you, You also need certain sort of patterning technique, because say you have a wafer and you want to deposit a material which has a certain pattern of this sort. If you don't have a patterning technique, it will be like a blanket deposition. You put the wafer and throughout the wafer the material will be deposited, but it's not the situation in practice. You need, say in a wafer you need 2 electrodes like this. You don't want the entire wafer to get deposited. If it is deposited with a metal or with any other material, then it's very difficult to make a sensor or a device out of it. In device you have different geometries. You need electrodes of this sort, then probably you need a deposition like this. So one has to pattern those, and that's why patterning technique is very important in microfabrication, device or sensor fabrication. So one of the most widely used patterning technique is lithography technique. Now just like other techniques, lithography technique also can be divided into or classified into different sectors. So one way to, or one technique associated with lithography is known as microlithography. Another lithography technique is known as soft lithography. So in microlithography technique, again we have UV lithography, we have electron beam lithography, then X-ray lithography and ion beam lithography. Now from the name itself it is very clear that based on the source you change or classify the lithography technique. So if the source of lithography is UV, ultraviolet light, we call it UV lithography. If it is electron beam, then it's electron beam lithography. If it's X-ray, then it's X-ray lithography, so on and so forth. So before we go deep into that details, just to give you an idea, lithography is nothing but, it's like a writing technique. For example, I have this substrate and I want to make a pattern. So you need to write something like this, or you need a pattern like this. So lithography is a technique of that sort. Now when you are making those patterns, you need different source. This can be a light that is falling on top of the substrate and then creating this pattern. This can be a laser, this can be an electron beam, or this can be, say, an ion beam. So based on that the lithography can be classified. So that is what it is written over here. And then we have soft lithography technique. So for example, particle replication in nanoveighting template, we call it print. This is a soft lithography technique. Then you have micro contact printing, we have microfluidic patterning, we have laminar flow patterning, then there is step and flash imprint lithography, then we have hydrogel template. These are all soft lithography. So just to give you an idea, if you have a substrate of, say, glass, and if you can make a mark using a diamond cutter, this is also a sort of lithography, because you are making a pattern on top of glass using a diamond cutter. Say this is the diamond cutter. If you have a glass, you just scratch it. Now if you scratch it straight, it will be a straight pattern. If you scratch it like in a zigzag way like this, then it will be a zigzag pattern on the glass substrate. This is also a kind of contact lithography, where you are using the diamond cutter as the source of making that pattern. Even while you write, say, using the any pen, using a pen on top of a white page, this is a kind of making patterns, or this is pattern of a certain material, because the ink is a material, so you are making pattern of that material. So lithography also helps us in making those patterns. As far as the deposition is concerned, we don't have any control over pattern. We can't deposit a material using, say, PVD in a certain pattern until and unless we have a pattern already. So we will see how these lithography techniques will help us in making different patterns on top of a substrate. So, in this lecture we will see what is a UV lithography and electron beam lithography. Other lithography techniques are also similar, and once you study these two types, you will understand more or less how others are also, what is the working principle of other lithographies as well. So, UV lithography and E-beam lithography are the ones that are usually used in different device fabrication and sensor fabrication. So, let us start with an photolithography. So, it is like an UV lithography only. Ultraviolet light is a kind of optical signal, you can call it photolithography as well. So, it is like UV lithography or photolithography. So, in photolithography we use light to print or transfer pattern on a substrate or on any thin film over a substrate. This is what photolithography is all about. It can be UV, ultraviolet light, it can be laser as well. So, this is what we do. This is what we use as a source of photon, like it can be UV or laser. Then this is useful for making interconnects, electrodes and devices. Now, just to give you an idea, say you want to make a Z shape on a substrate. So, for that purpose, what we can do is we can take help of a photomask. So, what is a photomask? Photomask is a kind of material that has that pattern on top of it. Okay. So, you make a pattern on a material where the rest of the material is like transparent to optical signal, but this part is like opaque. I repeat. So, what you do is you take a transparent material or transparent sheet and say by some means you create a opaque material or a pattern with an opaque material which is similar to this, a Z, and then you put the substrate underneath, and on top of the substrate you make a coating of a polymer. Say the polymer is reactive to light. So, what is the property of that polymer? The polymer hardens or softens when it interacts with light. To make it even clearer, say you have this is the side view. So, you have the substrate, this is the substrate, you create a thin film of a polymer. How can you create a thin film of a polymer? You take the substrate, you put certain material of that polymer, certain amount of that polymer on top of the substrate, then you spin the substrate. We call it spin coating. So, once the material is placed on this, say, circular substrate, and once you start spinning, because of the centrifugal or centripetal force, this material will start spreading on top of that substrate, and when it starts spreading, it will create a thin film like this. I hope you can visualize. Once this is created, now your substrate has a thin film of that polymer. Now, the property of the polymer is, if light interacts with that, say the polymer hardens, it becomes hard. Okay. Now, you have that substrate here which has a polymer on top, then you have the photomask or mask where the rest of the mask is like transparent, only the pattern is opaque. Then you shine, say, UV light or any optical signal. The moment you shine UV light on top of that, this pattern will create a shadow on the polymer film, and rest of the area will get exposed to the UV light or say a laser light, whatever it is. In this case, we can consider it as a UV light. Now, because rest of the polymer is now exposed to UV light, this area will get hardened, it will become hard, because we have seen the polymer has a property, when it interacts with a light, that is say a UV light, it hardens. Now, because this area is now hard, then if you put this material in a solution which say dissolves this polymer, the softer part will get dissolved and the hard part will remain on that substrate. So, you now have a pattern which is similar to this. This can be other way around. For example, if you take a polymer where the polymer softens when it interacts with UV, then wherever the light is getting exposed, this part will become soft and this will be a hard material, because this is not exposed to light, this part is not exposed to light, the pattern, the photomask creates a shadow. Now, once you put this into the developer solution which dissolves the polymer if it is not hard, then the rest of the area will get dissolved, the pattern remains on the wafer is this pattern. This is a pattern of the polymer. Now, if you want that pattern to be a metal, pattern of a metal, say gold, what you do is, if in the first process when other part is like polymer and this part dissolved and etched out, then you do a deposition on top, the metal will be deposited across it. So, the metal will deposited on the substrate in this area, because here the polymer is not present. In rest of the area, the metal will get deposited on the substrate on the polymer film. So, I repeat, when you deposit metal on top of this substrate, if this Z pattern is like washed away, then the metal will directly get deposited on the substrate because there is no polymer on it, and in the rest of the area you will find the polymers are present. So, the side view if I draw, it will be something like this. So, this part is washed away. When metals are getting deposited, here the metal will get deposited on the substrate and here the metal will get deposited on the polymer film. Now, again you put this into the developer solution where the hard polymer also get washed away. So, the developer solution will be a bit different than what we used earlier. Then once this polymer get washed away, the metal deposited on top also will get washed away. You will end up getting the metal on the substrate. So, you will end up getting say a gold pattern of this on the substrate. This is a typical photolithography technique. So, in this case we have two different component. One is the photomask and other is the photoresist. Photoresist is the polymer that we used on top of the substrate, right. So, photomask design can be made using a CAD tool. We have different computer aided design tool. So, you make a design of your choice in the CAD program and then you can make the photomask on a say polyimide substrate, on a say glass substrate, on a say chrome substrate using say laser cutting or different other techniques. And to transfer the pattern on a substrate, a thin film of photoresist is needed. That is, a thin film of polymer is needed, which I already discussed in the previous slide, right. So, these are the two things. The photoresists are usually a polymer material. The photoresists are sensitive to light. It will either hardens or softens upon light exposure. I have described both of them. Now, based on light response, a photoresist can be termed as positive photoresist or negative photoresist. For example, say here I have given you an example. If you have a substrate and then if you coat this substrate with a photoresist, that is this material, and then if you apply mask, these black portions are mask, and then if you expose the entire setup in UV light, so UV light will interact with the polymer in this region. However, below the mask, the UV light will not interact with the photoresist. Now, if the photoresist softens after it interacts with the UV light, then after you put the developer solution, you will end up getting this pattern, because these area will get washed away as it is shown over here. So, we call it a positive photoresist. So, in positive photoresist, you will find that the polymer is getting softened when it interacts with the UV light. Now, if the polymer is getting hard when it is interacting with UV light, you will find after development, whatever is exposed to the UV light will remain like this, and what was below the mask will get washed away, because this is relatively softer. So, then we call it a negative photoresist. So, in case of negative photoresist, the polymer will become hard when it interacts with the UV light or light. So, that is how we classify photoresist, and we coat photoresist on top of the substrate using a technique called spin coating. So, what is a spin coating? I briefly explained. If you have a substrate, it can be a square substrate as well. Then you put the polymer on top and then you spin the substrate at a higher RPM. Now, when you spin it, the material, if it is fluidic in nature, viscous in nature, it will start spreading on top of the substrate, and then it will create a thin film on the substrate. Usually, the photoresist thickness is maintained, say, from 10 to 50 micron. 10 to 50 micron is the typical thickness of the photoresist, and the substrate thickness is usually 200 to 600 micron. Now, you can actually vary the thickness of the photoresist just by changing the RPM and the time, because if you keep on rotating, as the time progresses, it will keep on spreading. So, the film will become thinner and thinner. So, you can optimize again the RPM, the rotation per minute, and the time you give it for rotation. Okay. So, if you optimize these two, you will be able to get a certain thickness. So, again you have to do some trial and error with an photoresist just to check what RPM and what time is suitable for this. In many cases, you can get these information from different literature. You don't need to do it again if you are following a standard procedure that is already reported in a literature. Okay. So, this is what photomask and photoresists are. Then there is another process which is known as mask aligner, an instrument which is needed if you use a, say, more than one mask in your device fabrication. So far whatever pattern we have shown over here, it is a single mask process. You just want one pattern to be deposited on top of a substrate. Now, say in your device fabrication, there are multiple patterns associated with it. So, what you have to do, for example, just I am giving an example, you have to make a Z pattern, you have to again coat this with certain, say, polymer, or you have to deposit, say, semiconducting material on top of it, and then you also need a top electrode somewhere here. So, you can't use a single mask to do that, because there is a deposition technique in the middle. Once you have to deposit the Z pattern, then you have to deposit your semiconducting material, then on top of the semiconducting material you have to deposit another electrode. So, in such a situation, first you deposit the Z pattern as we have discussed previously, then you say deposit the thin film of an active material on top of it. Now, on top of that active material you need this pattern to be deposited. So, you can use again a new mask and follow the process we have used over here, but in this case you have to align this shadow as per your requirement. You can't just randomly put it, because if this shadow is in this direction, then the electrode will be deposited in here. So, you have to align it. For that purpose also we need an instrument, because all these things are in micro domain or even sometimes in nano domain. So, in such a small feature you won't be able to control things. So, for that purpose you have to align the mask as per your requirement, and the instrument used for that is known as mask aligner. And then you follow the same procedure in order to deposit an extra electrode on top of the active material. So it's like a 2-mask process. First mask is for the bottom electrode, then you have the active material, then the second mask is needed for the top electrode. So it's like a 2-mask process. As we increase the number of masks, the complexity associated with the device will also increase. One of the target in device fabrication is to use less mask, as less as possible. Okay, you can't use say 10 masks in a device fabrication, because then the yield will be really low, because every time you have to align, if there is a small mistake in alignment, your entire device may not work the way you want. So that's why it's better to use as less mask as possible, but at times you can't actually get rid of a mask. In that case, you have to use. So there are 3 take-home messages. One is lithography is a patterning technique. We have seen that. Then various types of lithographies are there. It can be soft lithography, it can be microlithography. Then in microlithography also you have UV or photolithography and other lithography techniques. In soft lithography also you have different other techniques. Then we have seen a material which is known as photoresist, which is a polymer, and it is sensitive to light, and we take advantage of that. It either hardens or softens based on the property of that polymer. So most of the photoresists are commercially available. One can buy and then use it for device fabrication. In our next discussion, we'll be again discuss a few more patterning techniques. What are the different patterning techniques associated with microfabrication? Till then, thank you.